Hello, good morning. So, welcome to this session. My name is Pedro Felix, and for the next hour, I will be speaking about Kotlin Coroutines for asynchronous and concurrent programming. I'm a software engineer working mostly on backend systems, identity, HTTP, both in .NET and on the JVM, more recently on the JVM. I'm also a teacher at the Lisbon Polytechnical Institute. And for the last 7 years, I've been working on server-side HTTP systems that one way or the other have some sort of asynchrony. So I've worked with old models for asynchrony on .NET. I've worked with async-await. I've worked with JVM, with futures, with RxJava, with reactive streams, and also with Kotlin. So my presentation here is going to be a little bit biased for the backend. That's where I have most experience. So what is Kotlin? It's a static type of programming language. It was created by JetBrains, the manufacturer of excellent IDEs, such as IntelliJ and Rider, around 2011. It has excellent support or integration with the JVM ecosystem. So it's very easy to start using Kotlin on a Java project, for instance, using IntelliJ and using Gradle without any friction at all. So it's great. It's an Android official language since 2017. That means that, for instance, Google documentation typically also produces examples in Kotlin, and Kotlin is well supported on Android Studio. On the server side, it also has official support for Spring Boot, starting with 2.0 on 2017. So it's something that framework manufacturers are starting to adopt and to officially support on the JVM ecosystem. Kotlin also targets other ecosystems, namely there is now Kotlin for native platforms and also Kotlin for JavaScript. They are not so well developed, and in my talk I will mainly focus the JVM ecosystem. The last version is 1.3. It was released October 2018, and it was the first release where coroutines are a stable feature. They were available previously, but they were called experimental. Now they are stable, they have a stable API, they are fully supported in production. So, why asynchronous? What is the use case? What is the motivation for us to write asynchronous code? Well, first of all, blocking waits monopolize threads. So when something is waiting, we need to use a thread during that period. And all threads are costly. For instance, on JVM, by default, just for the stack of a thread, we use 1 megabyte. So threads are not lightweight, threads are costly, and some threads are more than costly, they are special. So I cannot do things with them. For instance, I cannot block the UI thread if I want my system to remain responsive. Other systems, such as, for instance, Node.js, have a single thread or a single apparent thread, which makes it even more special, so that I cannot even think on blocking code there. Just to provide you an example on the server side, assume that I have a service that accepts inbound HTTP requests and that during its processing consumes or uses an external dependency. Something that is rather common in this new brave world of microservices, where I have a service, exposes an API, and eventually needs to consume another API. And I have 500 requests per second coming in, and I need to use an external dependency that has a 2 seconds latency. That means that in average, I will have 1,000 threads blocking on I/O. 1,000 threads means 1 gigabyte just for memory. So on a given moment in time, if I take a picture of the system, I will have 1,000 threads doing nothing, but each one consuming 1 megabyte of memory. Is it possible to do better? Yes. namely taking advantage of asynchronous I/O. I can do asynchronous I/O. I can wait for those 2 seconds latency without blocking a thread. That is made possible by asynchronous I/O, which is available on almost all platforms. And in this case, I will not have any thread blocked during that time. This is very sensitive, and we may live with this synchronous code for a while, and the system can behave well until the day where in production the external dependency that we are using slightly increases the latency. And then we start having issues. First, our server starts accepting new requests because there aren't threads available to accept new requests. If I increase the number of threads that are available in the server, I start hitting memory limits. So it's something that we can eventually on development environments, even on production environments, may not be critical and the first, but if our external dependencies increase latency, we start having more threads blocked, and if we are using if we are using synchronous I/O, we'll have an issue there. Asynchronous is not the same thing as parallel programming. Most of the times I'm not trying to do something in parallel. I'm trying to do a synchronous flow, but I want to do it without blocking threads. So I may use asynchronous also to get some parallel behavior, but namely it's not the first goal of asynchronous. It's not to have parallelism, it's just to have scalability. Also, asynchronous typically will not make things faster. On most platforms, asynchronous I/O is slightly more expensive than synchronous I/O. Again, we don't want to make a single request faster. We want to make the system have better throughput because more threads are available. I want the system to be more responsive because I'm not blocking the UI thread. I want a better resource usage, and I want more stability. I want that my system continues to behave correctly, even, for instance, a dependency increases the latency of their responses. In the past, we had many models for asynchronous APIs, ranging from callbacks that we have in Java for a long time, and we have in Node.js, and we had in .NET using one thing that was the asynchronous programming model, the begin something and the end something that is still on delegates, on the delegate signature. More recently, we had the concept of futures. For instance, on JDK 11, the HTTP client is based on futures. In JavaScript, promises are rather common. And in .NET, we have task of T as the class to represent a future. We also have reactive streams as a generalization of futures. It started in the .NET world, but is more popular in the Java world with RxJava, and also in the JavaScript world with RxJS. However, all of these models present some issues. Let's take an example. So I have a simple for that does 3 iterations. It has an accumulator, which is an integer, calls a blocking operation, passing the accumulator, receives a result, does something with the result, and assigns it to the accumulator. So I have a loop, a blocking operation inside it, and I have a sequential flow. So there is a dependency between iterations of the loop, something that is typical to happen. Okay. If I try to use, for instance, futures to deal with this issue, I can, instead of calling a blocking operation, I call an asynchronous operation that returns a future. I get a future, but then I don't need the future. I need the value that is represented by the future. So what could I do? In Java, for instance, I could do future.get and obtain the value that is represented by the future. But future.get is a blocking operation. It's the same thing as in .NET doing task.result. I'm blocking until the result is available. Okay, so we can try to use a different thing. For instance, in Java, we have combinators that allow me to define a callback when the value is available. In the case of Java and the futures is then except. If it was in JavaScript, it will be then. If it was in .NET, it will be continue with. So, okay, I do that. The problem is that now that do something with, it's not in the scope of the for anymore. It's in the scope of the callback. So the for will continue without calling do something with, because do something with will only be called on the callback. So I needed to change the structure of my code, and the code doesn't work anymore because I need to remove things of the sequential for each or for. And in this case in this example, which is rather typical, where the iterations depend on the value of a previous iteration, using callbacks and using continuations introduces major changes on the way that I structure the code. So I like to say that callbacks, futures, observables do not fit well in the structure, in the classical structure of imperative code, where I have sequence of statements, where I have complex control logic with ifs and tries and fors. It fits well when I'm using a different style of programming, namely when I'm using function composition and I am using expressions and not sequences of statements. It's typical, instead of doing fors, I will do, for instance, a zip or a flat map or a map. They impose a different programming style. It's not necessarily bad, it's just an observation. It's a different programming style, which comes with a cost. Sometimes it's good, sometimes, for instance, it doesn't fit the team or the type of developers that we have, and introduces some issues. I worked in a recent project where we had a fully asynchronous pipeline. The good thing was that we didn't have any production issues with lack of threads, none whatsoever. So the system was always responsive. Threads were always available because it was completely forbidden to block a thread. So no one was allowed to do that. What was the problem? The problem was that the code was spread with flat maps. We were using our RxJava, and one of the core composition functions that we have in RxJava is flat map. And when I try to understand a business concern, to try to look into the code, to try to find how that business issue was being solved, all that I found was flat maps. Because structural issues that were, or non-functional issues required to do with asynchrony were spread around all the code. So the challenge here is to create code that doesn't block threads, because threads are costly and some threads are special, while still using the same classical imperative synchronous coding style, where I have a for, a if, I call a function, I receive a value. I don't receive a future of a value. I call a function, I receive a value. And I can code using the same principles that I always did. So how can this be achieved? A very popular approach introduced by C# a couple of years ago was to use async-await. And it's very popular. Not only C# provides async-await, but also JavaScript now provides async-await. I think Python also provides async-await. So, and other languages are considering variations of async-await to resolve the issue. And when I heard about Kotlin, and I heard about the fact that Kotlin was trying to solve this issue as well, my first reaction was, okay, they are going to use async-await as well, so it's going to be similar to C#. And if Kotlin had async-await, or the same flavor of async-await that C# and JavaScript have, it would be something like this. So I would have the same for. I would sprinkle that magical await after obtaining the future, which converts a future into the value that the future represents without blocking a thread. However, I pay a cost. I need to annotate the function with that prefix async, and the function still returns a future, which is something odd, because in the last line, I'm returning an int, but the signature of the function says that it returns a future of an int. So if it was in C#, it will be a task of int. If it was in JavaScript, it will be a promise. So I return a value, but the function returns a future of that value. And that async there is a implementation detail. And that aspect is going to be important when we compare it with Kotlin. So the async doesn't show up on the caller. It's just the way, it's just me informing the compiler that the compilation of this function needs to be done a little bit differently so that I can use the await operator. So when I'm using async-await, each function still returns a future. However, the calling function can use await to convert the future into the value that is represented by the future. And the async is a private implementation detail. However, Kotlin decided to follow a different path. And the path was based on the concept of coroutines. Coroutines are a rather old concept. I think the first historical reference that I could find is from 1963. And it says that a coroutine is a generalization of a subroutine, of a function, that can suspend and resume execution multiple times during its processing. And how is this concept, this rather old concept, implemented in Kotlin? There are 4 core concepts that I will go through during this talk. The first one is the concept of a suspend function. So this is the original code. I have a function, a for, a blocking operation. The blocking operation returns a result. I do something with that result. If I want to use coroutines in Kotlin, I just do this. I mark the function as being a suspend function, and then I make sure that that function that I was called is also a suspend function. That's it. Namely, 2 important things. There isn't no await inside, so I'm not using await. I'm just calling a function and obtaining a result. The IDE will notice that that call is going to be a special call, and we'll put a marker. If I'm using, for instance, IntelliJ, it will put there that marker, saying that that point is a suspension point. And also, the function returns an int. So the function does not return a future of int. The function returns an int. So I have a function that during its execution will suspend processing without blocking a thread, and it still returns an int and not a future of int. And also, I don't need to use await. I don't need to not forget to use await. If I'm in C#, not using await typically results in a compilation error because I have a task of T and I need a T. If I don't use await, compiler will shout at me. But for instance, when I'm in JavaScript, it's rather easy for me to forget about the await, and then I only get an error during runtime. Also, if I need to call this function, I'll call the function directly. So if I have caller1 calls example, example returns an int, and caller1 can use that int directly. The same thing if I have another suspend function, caller2, that calls caller1, that calls example. So straight, plain code. Not a future inside, not an await inside. What I have that suspend marker or that suspend modifier on the functions. And if I look, if I try to create a graphical representation of this, I have suspend functions calling suspend functions, and where each function returns the value that I'm interested on. So plain calls between suspend functions, plain types returns, no future of t, no await or no async needed, sequential by default, non-blocking by default. Perfect. So eventually we could end the session now, go have lunch. We just need to sprinkle suspend everywhere. Well, things are a little bit more complex than this. The first complexity point appears when I need to interact with legacy code. For instance, when I need to call a JVM function, for instance, the Apache HTTP client or the async HTTP client, which are not suspend functions. They do not provide suspend functions. They provide callback interfaces or callback-based interfaces or future-like objects. So how do I interact between suspend functions, where everything is marvelous and everything is great, with legacy APIs, and I always have legacy APIs? Well, the second concept is the concept of a suspend coroutine function. And most of the magic of coroutines is in this suspend coroutine. Let's look at the example. So I have the same for loop, but now I'm not calling a suspend function. I'm calling a legacy function that returns a future. So I have a future, but I need the value that is represented by the future. So how do I get from the future to the value that is represented by the future? I can try to use suspend coroutine. And suspend coroutine is a function that I call, and then I provide to that function another function that receives a continuation. And the first time that I saw this, I stopped and I said, what is going on here? So I have a function, I call it, passing a function, which receives a continuation. Okay? And what am I doing with that continuation? I'm using that continuation on a callback that I create. So basically, I'm using a future, so I have the then accept, which is a variation of a continue with. So what I'm doing is, okay, I'm passing a function. This function will receive a continuation, and I'm registering this continuation on the then accept of the future. And saying, okay, when the value is available, please resume the processing using this continuation. So I called suspend coroutine. Inside suspend coroutine, I called future then accept. And then the async thread is released. When, after 2 seconds, 5 seconds, 10 seconds, the future completes, it will call the second callback that is in green. It will be called on a different thread. And that thread will call continuation.resume. And that continuation.resume will return from the suspend coroutine function, or apparently return from the suspend coroutine function. So I enter the suspend coroutine function in the yellow thread, and I leave the suspend coroutine function in the green thread. In the meanwhile, no threads were armed, no threads were blocked. And then, if I have a for, the processing continues on the for. So, no major issue with that. However, if we look into that code that I added, it's not pretty code, it's rather complex code. It's perfectly normal that when you see this, you are puzzled. And having this in our code base, it's not nice. But it's rather easy to grab this code and put it inside, for instance, an extension method called await. And then I just do this. Async operation return future dot await. So the function returning future returns a future. The dot await returns the value of the future. without blocking. What is that await? Is it a language feature? No. It's just an extension function. Because in Kotlin we have extension functions, so I just write an extension function. And because in the JVM world we have so many different flavors of features, because we have CompletableFuture, we have ListenableFuture, we have defer result, I can just create extension methods for them and name it await, and then I just do await. What if I'm using an API that doesn't provide me with an await extension method? I do it my own. I do my own await, taking advantage of the building block, which is suspend coroutine. So you may now say, oh, but you said that awaits were not used. Yes, I said that awaits are not used, except when dealing with legacy objects, with functions that are not suspend, functions that are based on features, functions that are based on callbacks. And if you look into most Kotlin examples, since they are rather small, eventually you will see an await there, and you may start to think that, okay, I need to sprinkle awaits in my code. No. I may have a core of the code which is suspend, doesn't need awaits, doesn't need features. On the boundary, I may need to use await, or I may need to use suspend coroutine because I'm interfacing with something that returns a feature, or with something that is based on callbacks. Okay. So, the second issue that we have is that we cannot call a suspend function from a regular function. A normal function, a non-suspend function cannot call a suspend function. So everything is great and amazing if I'm inside suspend functions. When I go outside, I may need to use await. When I try to get in, I have a problem. And why do I have a problem? because when suspend functions are compiled into bytecode, they use a style of compilation that is called continuation passing style. And this means that the signature of the function is changed. If you go look into the bytecode that is generated after compilation of that function, I will see that it has a first parameter, which is an integer, but it has a second parameter, which is a continuation. And it is this transformation that occurs during compilation that makes it possible to have suspension points that don't block threads. However, this only works if I'm from a suspend function to another suspend function. If I am on a plain regular function, I need to use the third concept from Kotlin Coroutines, which are coroutine builders. So coroutine builders allow me to go from regular functions into the marvelous world of suspend functions. And what they do, a coroutine builder, what they do is create a coroutine and start the coroutine. So what is a coroutine? Because until now, I've only talked about suspend functions. A suspend function defines a state machine. A coroutine is an instance of that state machine. A coroutine builder creates and starts an instance of a coroutine. And I like to think of coroutines like very lightweight threads that don't take 1 megabyte of stack. And I can have thousands of them, but they are state machines that they are spinning after I start them. They are waiting for things to happen without blocking threads, but they are state machines. A coroutine builder is a way to instantiate and start a coroutine instance. And I have several coroutine builders. I have one that is called launch, when the coroutine doesn't produce any value. And the result value or the result type of a launch is a job. A job is similar to a task in C#. Why did Kotlin introduced yet another future-like object because Kotlin targets JDK 6 because of Android, and JDK 6 doesn't have CompletableFuture, so they had to create their own. Also, Kotlin aims to target other platforms. So if I'm using Kotlin native, I will still have job available, but CompletableFuture is not available on iOS, for instance. And I have async, which is a variation of launch when I'm using a when I'm calling a suspend function that returns a T, and it returns a deferred. A deferred is similar to a task of T. So the relation between job and deferred is similar to the relation between task, doesn't produce any value, and task of T that produces a value. So when a plain function starts a coroutine, it receives a future-like object. So I still have future-like objects in the boundaries because they are nice to interact with legacy components. In the core, I typically only have suspend functions. So let's look at a concrete example, a Spring controller handler. So I have a method, I have an annotation saying, so any GET request to /example should be handled by this method, and in this method I'm calling example1. If I do this, I get a compilation error, and the compiler says, no, 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 no. GetExample is not a suspend function. You cannot call a suspend function from a non-suspend function. Okay, I could try to add the suspend modifier on getExample. However, Spring, at least Spring 5, does not understand that, and it will not be considered as an HTTP handler. So I need to do this a little bit differently. I need to put there a launch. So what I'm doing is that the getExample will return a deferred result. What is a deferred result? It's a feature-like object from the Spring framework. And inside, I will do launch. When the example returns, I will set the result of the deferred result, or I will set the error result. So I will complete the deferred result there. Not pretty code. So if I look at this, so my logic is inside example 1, and I have lots of noise around it. However, again, this is Kotlin, so it is easy to extract this into infrastructure code. Let me go here and just create this. So I created a function called the sync handler that does this sync. It receives a block that is a suspension function of unit to T, and then my business code will look like get mapping to /example, getExample equals a synchronous handler, and inside I have the business code that I want to call. So I'm just saying that I have a regular function, and then I have a suspend function, and that async handler will do the mapping between both. The mapping needs to be specific to Spring. It uses a Spring-specific type, such as deferred result, but it's easy encapsulated on a function. So the idea is that I have a Spring handler, old world. I need to use a coroutine builder. I enter into this brave new world of suspend functions. If I need to interact with the synchronous I/O using a legacy framework or a legacy function that returns, for instance, a future, I use await. If I run this, I can see, for instance, that on the first green line, I see the handler starting, and it is starting on a thread from the container. In this case, I'm using Tomcat, so it's a thread from Tomcat. And then I can see that the other logs are done in different threads, are threads from a Kotlin thread pool. They are not being blocked, and in the end, I end the processing. As I've said, can we do better than this noise around the getExample? Yes, we can. We just create an helper, a sync function, or a sync handler function, and then we just annotate this. Since Kotlin it's very easy to do DSLs in Kotlin, so it's very easy to create an async handler that I can call like this. Okay. Coroutine scope. Last of the four, in my opinion, fundamental concepts of coroutines. And here, I think, starts another major difference between async-await and coroutines. The problem that coroutine scope is going to handle and to solve is not handled properly by async-await. And perhaps some of you will identify issues in the way that you are using async-await by identifying the problem that coroutine scope is trying to solve. And for that, let's consider that I set a timeout on the handler for 1 second. My asynchronous business logic takes 3 or 4 seconds, but I set a timeout of 1 second. Meaning that after 1 second, the Spring container will produce a response, a 503 response saying service not available. And that HTTP request response flow will end. And I can see that on the green line, if I look into the logs, on the green line, on a thread from the Spring container, it is saying timeout. Okay, but if I still continue if I look into the logs, I see that, after 1 second, after 2 seconds, I still have the coroutine doing things. The request already ended, but the coroutine is still doing things. It will produce a value, which is going to be ignored because the response was already produced, but the coroutine is still spinning. I like to visualize a coroutine as a flow of executions where each execution can happen on different threads. That's why the different colors. Between those threads, we have the suspension points. Suspension points do not block threads, which is good. A coroutine builder just creates this instance and makes it spin, returns a future that represents the coroutine. However, the life cycle of that coroutine is detached of the life cycle of the thing that created the coroutine. In this case, I have a request. I was handling the request. While handling the request, I created a coroutine. The request was cancelled due to a timeout, produced a response, but nobody warned the coroutine. The coroutine is still there doing things. And some of the times I have these things on my code. I don't notice because they seem harmful, but they are spending resources. In Kotlin, this only happens if I use one thing that I will show later. But before that, for Kotlin to handle this, they introduced the concept of a scope. So when I use a coroutine, when I use a coroutine builder, I always use a coroutine builder in the context of a scope. I can use a special scope, which was the one that I used before. I think that, let me see, it's here. So the first yellow line, you can see global scope. Global scope is a particular type of scope that is global, meaning that the coroutine that I create on global scope is not going to be attached to anything. It's like a daemon thread. Most of the times, I should not use global scope. I use it here just as an example, and it's due to the fact that I'm using global scope that I have this coroutine leakage. The result, the response is produced, and the coroutine still keeps spinning. So, scopes allows me to have parent-child relations between coroutines. So I can have, so because a coroutine is also a scope, when I launch a coroutine inside another coroutine, it will be in the same scope as the parent. Why is this scoping important? Why is this parent-child relationship important? Because it allows me to automatically propagate cancellation. So if the top coroutine, the one on the left, ends, for instance, it is cancelled, it will propagate cancellation to all the child coroutines. Okay? And the inverse also happens is if one of the child coroutines throws an error, that error will propagate to the top one, which will then cancel everyone else. So I have a way to stop everything that is bound to a specific scope when that scope ends. When we deal with this, the major question and the hard question is, but what the hell is a scope? In my application, what should I use as a scope? The answer is, it depends. For instance, if I'm using an Android, if I'm doing an Android application, perhaps activity can be used as a scope. Because if I launch an activity and then I press back, the activity ends, I want all the coroutines that were created in the context of that activity to stop. I left the screen. I don't want the coroutines to still be spinning after I left. Or I may want to associate the scope to other concepts, because I may want to leave the activity but have a data model or a service that keeps fetching information, and I want to associate the coroutines to that service. It depends on the architecture of the application. For instance, if I am on the server side, a good choice for a scope is the HTTP request. If I create coroutines in the context of a request. The request ended, I want to end all the coroutines. They don't have any reason to remain alive because the scope where they were created was terminated. So a scope, it depends on the context, and it's a thing with a life cycle, and we want to correlate, to associate the life cycle of the coroutines with the life cycle of that thing. I have here an example using a scope for Spring, taking advantage of the deferred result scope. So Coroutine Scope is an interface. To implement that interface, I just need to provide a getter with a job. That's it. And in this case, what am I doing with the job? I am registering a non-timeout handler on the deferred result scope, meaning that when the request times out, Spring will call that handler, and I will cancel the job. And that will propagate that cancellation through any coroutines that were created on that scope. Directly created or indirectly created. And if I look into the logs, what I can see is that on the first yellow line, Spring did timeout. And immediately after, on the green line, I have the coroutine being cancelled and everything stopping in a couple of milliseconds. So all inner coroutines will be also cancelled as long as scope is properly propagated. Namely, as long as global scope is not used. And global scope is an easy thing to use because it's a global object. So, okay, I need to launch a coroutine. I call launch. The compiler screams at me saying, no, no, no. To launch something, you need a scope. I need a scope. What can I use? Oh, there is global scope. Global scope.launch. Done. It works. More or less. It works, the coroutines are created, but the coroutines are not properly managed. Because when the scope ends, the coroutines will still be there spinning. So, okay, how does async-await handle this issue? It doesn't. So, async-await does not handle this issue of proper cancellation. Well, in C#, more or less does it, because in C# we have the concept of cancellation token that I can pass, and then I can observe, and if the cancellation token is active, or if cancellation was requested, I can cancel my code. However, it's not a very clean solution, because I need to remember to always pass the cancellation token to everything that I called. So cancellation token needs to be viral. I call a function, I pass it a cancellation token. Any function that function calls needs to pass the cancellation token so that the cancellation token is available on all the tree of asynchronous functions that I called. So it's a model, but it's not a very good model. In JavaScript, there isn't any model, because in JavaScript, there isn't any predefined way of canceling promises. It's under specification, but there isn't any consensus yet. So I don't have any solution here. I think most of the code bases have this problem. However, the effect of this problem most of the times is hidden. I still have things running, but since the result is ignored, so it doesn't affect a lot. It's just wasting resources. But proper cancellation is something that doesn't exist. In JavaScript, more or less exists in C# using cancellation token. In Kotlin, it is a first-class concern. Okay, so how about concurrency? In the name of this talk, I've talked about asynchronous processing, but also about concurrency. Well, what is concurrency? Concurrency is the access by multiple threads to mutable shared data. Meaning that when multiple threads access mutable shared data, it needs to have proper synchronization. What is proper synchronization? It depends, but I may need to use locks, I may need to use synchronized in Java, I may need to use monitors or smuffers in Java. Well, it depends on the exact type of access that I'm doing, but proper synchronization needs to be in place. And how about with coroutines? Because coroutines execute in different threads. So, do I have a concurrency issue when using coroutines? Do I have to explicitly add proper synchronization? No. Because on a coroutine runs in multiple threads, but runs sequentially on the multiple threads. And the coroutine engines ensures that from a memory model viewpoint, there is an happens before relation between the threads, meaning that yes, I have multiple threads accessing mutable data, but on a sequential fashion, meaning that there isn't any concurrent access. I don't need proper synchronization. Okay. Which is good to know. So I can think of a coroutine from a synchronization viewpoint as a single thread. However, if I have multiple coroutines accessing the same data, for instance, classical example, I'm doing requests to the outside, so I have incoming requests, I'm doing outside requests or outbound requests, but I want to use a cache for the outbound requests. A cache is going to be mutable shared data. So each incoming request will produce a coroutine to go outside. I will have multiple coroutines trying to get things from the cache, trying to insert things into the cache. If I have multiple coroutines, I have concurrent access. So I need proper synchronization. Okay? Only if I have multiple coroutines. How can I handle this proper synchronization? Well, the story right now, it's not clear enough. One thing that it's true is that we need proper synchronization. Beware that if I try to use the traditional synchronization mechanisms that I have on our platforms, I may run into issues because most of the traditional synchronization primitives are blocking. So if I try to use a smuffer, it will block. For instance, in C#, I have, I think it's Slim smuffer or smuffer Slim that provides asynchronous operations, operations that result on a task of something. In Java, we don't have that. However, the Kotlin library already provides me with something. One of those somethings is a mutex interface that provides mutual exclusion, where the lock method is also a suspend method, meaning that I can acquire a lock and not block a thread while waiting for that lock to be available. Also, Kotlin, or one of the Kotlin X libraries, I was going to say the standard library, but I don't think it is the standard library. It's one of the extensions that are under the package Kotlin X, also provides me with a channel interface. And this channel interface is like a queue and provides me with a suspend send and the suspend receive, meaning that I can send things to a queue, I can extract things from a queue without blocking while sending or receiving. Namely, what the Kotlin team is trying to create, and it's still experimental in Kotlin 1.3, is to use a technique where we handle the issue of synchronization by not having shared state between coroutines. So what they are recommending is that I confine shared multiple data to a single coroutine. So if I have a cache, I don't have multiple coroutines trying to put things inside the cache and grab things from the cache. I have a single coroutine that owns the cache. The cache is private to that coroutine. And I have other coroutines communicating with that coroutine to grab things off the cache and put things there. So it's a nectar-like programming model where mutable state is private to a nectar, and what is a nectar is a coroutine. It's still experimental in 1.3, meaning that there is something available, but it is highly likely that the signatures, the programming model will change. One important thing to bear in mind is that a coroutine should not block threads, and we can have thousands of coroutines. So having, for instance, a coroutine handling a cache is not the same thing of having a thread handling the cache, because a thread is costly, a coroutine isn't. Okay, almost ending up. Just to highlight some differences between the async-await model and the Kotlin model. This example is based on an example by Roman Elizarov on Kotlin Conf 2017, I believe. On the left side, I have the async-await model. On the right side, I have the Kotlin model. And the example is an example where I need to load two images and then do something with both images. If I want sequential non-blocking processing and I'm on C# or JavaScript, I need to put the await. So I do load image, I receive a task of an image, and then I do await. I do a second load image, I receive a task of an image, and I do await, and then I do something with the images. If I'm in Kotlin, I just called load image, because load image is a suspend function, so I just call load image. So, by default, in Kotlin, the behavior is sequential. However, by default, the behavior when using async-await is not sequential. If I look into the lower part, if I called load image, so I said f1 equals load image, f2 equals load image, and I don't do the await, I will have both load images running. So, without putting there an explicit await, the default behavior is parallel. For instance, if load image access shared data, I will have a concurrency issue there. So by default, on an async-await model, I have concurrency issues. You may ask, but what if I want to do the same thing in Kotlin? Can I do it? Yes, but you need to be explicit about it. You need to create two coroutines that will execute the first load image and the second load image. In this case, since the coroutines are returning something, I need to use the async function. Okay? So, if I want concurrent parallel behavior, I need to explicitly require it, which is, in my opinion, a safer approach. So, concurrency is explicit. Not only concurrency is explicit, I need to turn it on explicitly by calling async. Concurrency is structured. And what does this mean? It means that when I'm branching out, creating concurrency, I'm doing it in the context of a scope. Namely, I can only call async if the context where I am already has a scope. So, meaning that those async calls that I have there on the right side are being called in the context of a scope. Meaning that if the scope where I am is cancelled, those load images will be automatically cancelled as well. And if you look, there isn't any cancellation token inside. The cancellation of the load image will happen automatically if the scope where those async calls was done is also cancelled. So they call the Kotlin engineering team called this structured concurrency. So 4 major concepts, in my opinion, when reasoning about coroutines: the concept of suspend functions, the concept of a suspend coroutine as a very generic building block that I can use to interact with the external world that is based in features and based in callbacks. The concept of coroutine builder as a way to start, to create and start a coroutine. And finally, perhaps one of the most important concepts, and one of the concepts that is more different of the one that is provided by async-await, is the concept of coroutine scope. And the idea that unless I'm using a global scope, everything runs bounded to a scope, and that scope will imply propagation of cancellation. So, some resources. I have these examples on my GitHub, PMHS Felix, on Kotlin Coroutines. I will put the slides there. I have a previous version of this presentation that I did on another context. They are there, but I made some changes for today. I'll put them there as well. I strongly recommend 2 videos by Roman Elizarov, which was one of the engineers behind Coroutines, on Kotlin Conf 2017 and Kotlin Conf 2018. Namely, there are 2 videos on the 2017 edition which are very worthwhile to see. There is also a Coroutines guide that talks about these things. And if you want to look this in action, JetBrains is creating a new web applications framework. It's called Kitor. And everything is Kitor is around coroutines and suspend functions. So if I'm using Spring, the core of Spring doesn't use suspend functions. So I need to interface between callbacks and futures and suspend functions. If I'm using an HTTP client, probably the HTTP client from Spring, for instance, it's not a suspend function. So I need to use a wait to interface with it. In Kitor, almost everything is suspend because it is a web applications framework that was done from the beginning using this model. And I think it's time to have lunch. Thank you very much for being here. Any questions that you have? Questions? Yes. Well, the only tooling that I know is that they provide hooks into the logging frameworks to show what is happening. So when, because now, typically logging frameworks log the thread that issued the log. But now I have two different concepts. I have the concept of thread and I have the concept of coroutine. And I want to know the thread, but more importantly, I want to know the ID of the coroutine where something happened. So they instrument the logging so that I have information about both. If I have some profiling that detects blocking code, well, what I can speak from my previous experiences, not using coroutines, but using other asynchronous programming model, is that first, it's code review. So, and an explicit rule, you cannot block anything. Sometimes we need to block because you are using legacy APIs that don't support async IO, but each case is a case that needs to be analyzed. By default, we don't block. Another good way of detecting places where we are blocking is configuring thread pools with very, very few threads. So, and if I configure, for instance, I used to run the Apache HTTP client with only 2 threads, or as many threads as CPU cores. Since they don't block, I don't need more threads than CPU cores. If any one of those threads blocks, I will notice. So yeah, I don't know any profiling tool that triggers a warning. So in the past, I've used mostly peer review and doing non-functional testing with very few threads. Thank you. Any more questions? No? Once again, thank you for being here.